can see it. And well, first of all, I want to thank Joao, Silvia, and the Center for Philosophy of Science at the University of Lisbon for having me here once again. And well, I was saying before that for me, coming to Lisbon is really not traveling abroad, but it's like coming home. And especially coming here to the center where I spent so many good and interesting moments in my career. And well, I'm also quite honored to be the first speaker in this joint effort that is the IBERIAN network for the philosophy of sciences, something that really started in September. So this is a really new thing. And well, I'm just honored, and I hope to be up to the people, up to the expectations. But I have to say that this is something, I mean, I don't feel as a specialist talking today, but more as a student, because this is some new topic I've been working on now for only a few months. So I really do not control everything I'm going to say. So, but I think that the permanent seminar in philosophy of sciences started also as an idea of presenting some work in progress. So I think that in this sense, it is a good idea to do that. So, okay. Feigning hypotheses, non-Newtonian approaches to gravitation. In the optics, Newton said, the main business of natural philosophy is to argue from phenomena without feigning hypotheses. Okay, this is precisely the motto I'm trying to contradict in this talk. As many of you probably know, Newton tried to establish a method without feigning a hypothesis, and all his reluctance to use a hypothesis is well known. But I will try to show that hypotheses were used in natural science after Newton in the 18th century, and that there may even be actually good reasons to use a hypothesis. So the aim of the talk is to understand some alternative explanations of gravitation and to show the problematic status of the notion of force. So the idea is, well, the notion of force is problematic because we really do not know how force is transmitted or how it acts on bodies. And the focus is some explanations of gravitation that start from Newton's idea, but they make use of a hypothesis in the 18th century. So I will show the work of some 18th century natural philosophers who explicitly acknowledge the use of hypotheses to solve some problems in Newton's work. And of course, 18th century is a big century for natural philosophy, so I will restrict my talk only to two of that theories, which are Euler and Lesage. Leonhard Euler is a well-known mathematician, and Georges-Louis Lesage is a not well-known Swiss natural philosopher. But I will introduce you to him. And also, I have like a larger aim, which is, I mean, it's like in the background or in the underground of my ideas, which is to show the richness and problems embedded in what has been named classical mechanics, and to use this richness and these problems to challenge the idea that classical mechanics is a stable discipline, as it has been sometimes told in common historiography. Of course, many scholars have challenged this view, and this is, I'm not doing anything revolutionary, but the idea is to contribute a bit to that challenge. Because I think that to recover some theories from the past can help us to understand the standardization of some concepts in history and philosophy of science in general. So I aim to show the conceptual instability or the variability of concepts in classical mechanics. Okay, these are the, besides Newton, of course, these are the two protagonists of my talk. And Franz van Lunter said that Euler and Lesage were the most reputable continental advocates for a mechanical explanation of Newton's universal gravitation. So von Lunter's statement is actually one of my reasons to focus precisely in these two figures. And I have another reason, but I will only reveal this reason at the end of the talk. So I leave you with a bit of suspense, at least. Okay. Euler, of course, is a very well-known figure, but his ideas on gravitation were mostly forgotten, and there are several reasons why they were mostly forgotten, but they were also recovered sometime later. And okay, as I said before, Georges Lesage is a pretty unknown figure. He's a Swiss natural philosopher born and raised in Geneva. He was more or less 17 years younger than Euler. And it is curious because he corresponded with much of the intellectual elite of the time, including Euler. Okay, so after this short introduction, here is the plan of the talk. I will expose the main problem, and then I will present Euler's theory, I will present Lesage's theory, and then I will make some final remarks. Okay. The problem. So this is a well-known paragraph, but I don't know if all the audience is familiar with the Principia. And Newton here says, hitherto we have explained the phenomena of the heavens and of our sea by the power of gravity, but have not yet assigned the cause of this power. This is certain that it must proceed from a cause that penetrates to the very centers of the sun and planets without suffering the least diminution of its force, that operates not according to the quantity of the surfaces of the particles upon which it acts, as mechanical causes used to do, but according to the quantity of the solid matter which they contain, and propagates its virtue on all sides to immense distances, decreasing always as the inverse square of the distance. Gravitation towards the sun is made up out of the gravitations towards the several particles of which the body of the sun is composed. So, this paragraph is part of the General Scholium that was added to the second edition of the Principia in 1713. And here it is clear that gravity acts according to the inverse square law. So it is directly dependent on the quantity of mass of the bodies that attract each other, and inversely on the distance which lays between each other. So it is a power that mathematically works in that way, but also physically it works according to the quantity of matter the matter of a body, affecting equally every part of the body till the center of it. And so, okay, we have it mathematically and physically, but it only remains to be explained the origin of this power. So the cause that generates it. And the Principia, as Newton himself recognized, explain the how and not the why. So we know how the force acts, but we do not know why it acts in this way. And I want also to stress here the dismissal of mechanical causes of gravity in this paragraph. But okay, if we consider the optics, we have another famous passage here, the 21st query of the optic. And here he says, is not this medium much rarer within the dense bodies of the sun, stars, planets, and comets than in the empty celestial spaces between them? And in passing from them to great distances, does it not grow denser and denser perpetually, and thereby cause the gravity of those great bodies towards one another and of their parts towards the bodies, everybody endeavoring to go from the denser parts of the medium towards the rarer, if anyone should suppose that ether, like our air, may contain particles which endeavor to recede from one another, for I do not know what this ether is, and that its particles are exceedingly smaller than those of air, or even than those of light, the exceeding smallness of its particles may contribute to the greatness of the force by which those particles may recede from one another, and thereby make that medium exceedingly more rare and elastic than air, and by consequence exceedingly less able to resist the motions of projectiles and exceedingly more able to press upon gross bodies by endeavoring to expand itself. So it points out a possible cause of gravitation by a rare, dense, and elastic ether. And so the ether poses the question of a mechanical medium. And although considering Newton a supporter of mechanical philosophy, I know it is still a controversial issue among Newtonian scholarship, there are at least some elements in the way Newton proceeded that can be associated, of course, to mechanical ideas. In the preface of the Principia, he states his intention. I wish we could derive the rest of the phenomena of nature by the same kind of reasoning from mechanical principles. Okay, we might not be sure about the cause or about if it is material or not, and there might be a subtle medium or it might not be. But by rule 3, we know that gravity is not a mechanical quality, not that I affirm that gravity to be essential to the bodies. By their vis incita, I mean nothing but their inertia. This is immutable, and their gravity is diminished as they recede from the earth. So gravity does not keep the mereological relation held by the mechanical qualities of the bodies as inertia, extension, and impenetrability do, because essential qualities of the bodies are immutable and gravity decreases with the distance. Also in query 28, he says, and for rejecting such a medium, we have the authority of those, the oldest and most celebrated philosophers of Greece and Phoenicia, who made the vacuum and atoms and the gravity of atoms the first principles of their philosophy, tacitly attributing gravity to some other cause than dense matter, till we come to the very first cause, which certainly is not mechanical, and not only to unfold the mechanism of the world, but chiefly to resolve this and such like questions. So if there is a medium, that this medium acts mechanically, if not, how? Or how does non-mechanical matter act on or interact with mechanical matter, with regular bodies? And also, one cannot forget that in Newton there are some reference to God as a first cause, or as this non-mechanical cause of gravity. So throughout the Principia, Newton refrains from expressing his own views on the nature of gravitation. Philosophically, we could say that he tries to avoid making ontological commitments in this sense. And this is also the position in this famous letter to Dr. Bentley, where he says, it is inconceivable that inanimate brute matter should, without the mediation of something else, which is not material, operate upon and affect other matter without mutual contact, as it must, if gravitation in the sense of Epicurus be essential and inherent in it. And this is one reason why I desire you would not ascribe innate gravity to me, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by through which their action of force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial is a question I have left to the consideration of my readers. So, Of course, this was not known by many Newtonians at the time or many natural philosophers, but Bentley expressed these ideas in the famous Boyle lectures, advocating for a divine cause of gravity. But in any case, basically, we are left with certainty and at least apparently contradictory views. Sometimes there is no ether, sometimes there is. And we are not sure if this ether is mechanical or it is an active fluid or whatever it is. So taking into account all the ambiguities, the problem is of course an open question. How was this received by the community? Okay, some parts of this are very well known, others not so much, but in any case, I am going to be very brief in this part. And this is more about the reception of universal gravitation than about the Principia. The Principia were well received in Britain since the very beginning, but the cause of gravity was problematic. So the Cartesians at the beginning rejected the work, of course, and the main ideas, because they defended this vortex theory to explain gravitation. But later, some Cartesians at the beginning of 18th century considered criticisms to vortex theory and tried to adapt it to the inverse square law and to make vortexes compatible with Kepler's laws, more or less from the 1720s onwards. So, and then we have also the position of Huygens and Leibniz and the Wolffians, and we can say that both Huygens and Leibniz rejected the mutual attractions of all parts of matter, which is one of the main ideas in Newton. And Leibniz at the beginning did not state a clear cause in principle, but later on he was inspired by some models of Gilbert's work on magnetism. But as a summary, by the 1740s, more or less one can say that Newton's opponents are in a defensive attitude. And because if we take as an example of what was happening in the continent, the Académie des Sciences of Paris, by 1750, the Academy does not admit vortexes, and in 1760, vortexes are out of the university circles in France. Well, in Germany, the story is different and a bit more complicated, but I'm not going there. Okay, what happens in the second half of the 18th century? So, okay, there is a kind of elimination of forces acting at a distance, or more or less an agnosticism regarding the cause of gravitation. That by what we can call Newtonians or well, people familiar with Newtonian theory and defending the inverse squares law, except of course Laplace, who one can say that is the champion of action at a distance and applied this action at a distance almost to everything. So D'Alembert, Exleben, and people like Muschenbroek or Gravesand have this agnosticism, but stated strongly that the cause was in any case not mechanical. And it is funny what happens in Britain, but there is as the ether and the vortexes are going out of the continent, they fly to Britain or something like that. And there appear some British ethers, one can call that, in people like Robinson, Maclaurin, Joseph Black, and Colden, based on the idea of voluntarist theologies, which are inspired partly in the inquiries in the optics. And well, one can also talk about Kant, which in his work on natural philosophy in the Anfangskunde, he says that active and repulsive forces are fundamental, but if we go to the opus posthumum, the ether appears there. Okay, I'm not going to comment on Kant because then I will not talk about anything else, but well, this is more or less the picture. and of the reception. And then I just go to the main points. So I will consider Euler's latter conception, because one can say that there is an evolution on Euler's ideas on gravitation. And so I will focus mainly on the Untitled Chapter, the guide of natural philosophy, and also in the letters to a German princess. The Untitled Chapter was not published in Euler's life, maybe because I think that one possible reason is because he considered that the theory of gravitation was not complete. But the letters, and it was not published until 1862, so until the second half of 19th century. But the letters to a German princess were actually very popular. In his early conceptions of gravitation, Euler derived from forces from inertia, but later on he expressed differently his commitment to mechanism. He considered that forces are not primitives. I think that because he wanted to separate his view from that of Leibniz. And forces are derived from the impenetrability of the bodies. So the impenetrability of the bodies lies more or less in the metaphysical, as a metaphysical foundation of matter and of part of Euler's natural system. And to Euler's, forces are not in the bodies, but they are like emergent properties. Forces emerge when bodies try to interpenetrate each other. One can say also that Euler is one of the contributors to the establishment of Newtonian philosophy, or no, sorry, not Newtonian philosophy, Newtonian theory in the continent, but not regarding the philosophical implications of Newton's ideas, because he explicitly rejected the idea that bodies attract each other. Not in his, not as a young scholar, apparently in 1723 he defended this view, and in his Mechanica in 36 he was kind of ambiguous, but later on he definitely rejected this view. So there are certain properties we cannot measure in the impenetrability of the bodies. That is why one can say that it's more or less the metaphysical foundation of the system. But there are other essential properties to ordinary matter. So inertia is one of the properties, and it is measured through mass. And extension is another of the essential properties of matter in Euler, and it is determined by geometry. And ordinary matter is also highly porous, and it is incompressible. And then we have another kind of matter, which can be called this subtle matter, which is the ether. And it is a subtle compressible fluid that has low density to allow the motions of the planet. So according to Euler's conception, the ether does not act, or almost not, on regular bodies. But when the ether is compressed, it emerges a force, so a pressure, that is responsible for the forces that cause the motion of bodies. The ether is also a continuous fluid, so it is not composed of tiny particles. It is not atomic in this sense. One can say that it is like a perfect continuum, and the continuity of this fluid is required for the ether to be able to exert its pressure in every direction. Okay, this is a quotation from the Enlightened, and Euler says, all bodies in the world consist of these two types of matter, the coarse and the subtle. So as the coarse matter is highly porous, sorry, I get distracted. As the coarse matter is highly porous, the subtle matter, the ether, penetrates the rest of the matter. And all differences between them arise from the different mixing and composition of these two types of matter. And since our two kinds of matter can be mixed and compounded in an infinite number of ways, it is easy to see that through this process, the variety we observe in the bodies of the world can come about. Since from general experience alone, we have determined the existence of two types of matter in the world, and also the unchangeable density of coarse matter, we must also rely on experience in examining the particular properties of subtle matter. So, okay, what Euler shows is more or less the impossibility of everything filled with ordinary matter and the impossibility of the vacuum. And from this, he derives the existence of two fundamental different kinds of matter. I'm not sure if we can call that this is an deduction or from general experience, but this is more or less the idea. And here I want also stress that Euler is very explicit in this, in the distinction of these two types of matter, which in some sense I think that is a distinction with Cartesian philosophy, because in Descartes we had these three elements, but matter is just one, because matter is the essential property of matter is extension. And I say this because Euler has many times been characterized as a Cartesian, and I think that the picture is much more complex than just Cartesians, Newtonians, Leibnizians, but maybe in the 18th century we have even more programs than just these three. Okay, more on the theory. So the ether has some physical properties. So it is not infinitely, it is compressible, but it is not able of infinite compression. It has inertia and it has a finite density. And like a normal fluid, the ether strikes to reach equilibrium. As everybody knows, so Euler mastered hydrodynamics, and he used his works on hydrodynamics as kind of a model for this ether. And from his ballistic studies and hydrodynamic studies, he learned that a body traveling in an infinitely fluid and elastic medium would experience almost no resistance. And this is the key, because in the second book of the Principia, the impossibility of Cartesian ether is shown, because it would, the planets, it would exert some resistance, and then the planets would not be able to move, to make the motions they make. So this infinitely fluid elastic medium fulfilled the required features of Euler's ether. And as I said before, ether as a regular fluid strikes to be in equilibrium, so it is actually not in equilibrium. And that is the reason why there is a planetary motion, because otherwise celestial bodies would just float on the fluid and stay still if it was in equilibrium. So when there are these differences of pressure, the bodies are not equally pressured, and the bigger pressure will work in the direction of the motion. This is a pretty basic idea. If I press something, it would move in the direction I'm pressing. So the bodies, when pressured or pressed, move to some areas where the pressure is less. And here is the way he explains the fall of bodies on Earth, because in the surface of the Earth, there is less ether than in the upper parts of the Earth, so the bodies fall. And also, it is shown by experience that the farther the bodies from the Earth, the smaller their weight. And the weight of the body decreases in inverse proportion to the squares of the distance. So in some sense, the pressure of the air must work also according to the inverse square of the distance. And okay, the mass dependence of the law. From hydrodynamics, he derives incorrectly, as van Lunteren has shown, that the resulting force upon a body would be proportional to the total volume of the ultimate particles of homogeneous gross matter, and accordingly proportional to its mass. So he deduces that the pressure exerted on a body is proportional to the mass. But to do that, he establishes the proportionality of mass and volume, which is actually not done in a correct way. But anyway, and What is also interesting about Euler's fluid ether is that in some senses it is similar to the modern conception of potential in a field. And of course, the idea of field is also partly taken from an analogy on electrodynamics, and this is also a well-known history. So, okay, more on the theory. Apparently, there are some physical consequences, and the resistance of the ether seems to explain the apparent secular acceleration of the Earth. This would be a positive consequence if it not were for the fact that it is almost a perfect fluid that offers no resistance. So in the end, I'm not sure if this is really a consequence from the theory or just something that Euler says, but he had a bit of a contradiction in the Untitled. And of course, the theory has some problems because it is not clear how celestial bodies move through the ether and cause a decreasure of pressure according to the inverse square law. And here, Daniel Bernoulli raised an important objection and said that Euler required a closed space, like a closed universe, to keep the pressure in the way Euler needed the pressure. And the problem is also that Euler had said in the Euler acknowledged this objection by Daniel Bernoulli, but in the Untitled he had said that the space was infinite. So I mean, we have maybe good reasons why Euler didn't publish this work. And there is also an incompatibility of his optical and gravitational ether. So he would require at least two fluids, one to explain light and the motions of light, and another to explain gravitation. This objection was raised by Lesage, and Euler also acknowledged it. There is some incompatibility with the principle of action and reaction, because it would seem that the bodies would not respond immediately would not react immediately to action, but the action and reaction would have to travel through the ether, and this would be also a problem. And also the problem that at least we have two kinds of matter. I say at least because maybe there is a second ether, which is the optical one, and so on. But what are the reasons to propose a theory? Of course, the obvious one is the commitment to mechanism and the idea of trying to avoid action at a distance, which was always problematic. But I have also read that there might also be religious reasons in Euler, because the existence of the ether precludes the stability of the solar system. And this implies, in conformity with creation, a beginning and an end of existence. I don't know really the details of this. I have just read this, and I think that is also interesting. And there is also a praise of hypotheses. Euler explicitly says in 1743 in his work on magnetism that sometimes hypotheses are necessary to attain the truth, especially when we do not have other media. And if we want to consider the methods he uses and to consider also the 18th century as a non-uniform period according to the methods used in natural philosophy, he used very much the analogy. Of course, magnetism is a source of analogy in gravitational cases, but also hydrodynamics. He used also his empirical studies on fluid, and of course, he used hypotheses. Okay, now Lesage theory. Okay, I present here the sources, the Lucrèce Newtonian and the Traité de physique mécanique. These are works that were not published in Lesage's life, but these works circulated because he sent them to his correspondents. And there is also the Essai de chimie mécanique, which was published in 1758. And this essay actually won an award in the Academy of Sciences of Rouen because it was able to explain chemical affinities by mechanical causes, which is not my topic today, but it is also another interesting topic in the 19th century. And in the Lucrèce Newtonian, which is, I think, a very interesting title, the Newtonian Lucretius, he expresses the deep impression that the reading of Lucretius, the Rerum Natura, caused on him. How is his gravitational theory? So Lesage proposed a kinetic corpuscular physics, and his theory of gravity is very inspired by an analogy with light. He actually says that the light permeates all the bodies, even the harder ones, like diamond, for example. And so does gravity. And he says even more than light, because gravity also penetrates in dull bodies, in dark bodies, who actually light cannot. And the interstellar spaces are full of subtle low density particles traveling very fast. And Lesage names this particle corpuscles ultramundane, so ultramundane corpuscles or otherworldly corpuscles. And they are ultramundane, he says, because they are coming beyond the limits of the visible world. That is where the name comes. And the metaphysical foundation is atomism, and it is also curious that he considered himself as a Newtonian. And in fact, he and his disciples named themselves as the true heirs of Newton. He was quite impressed by the Leibniz and Clark correspondence, especially when Clark said that every philosopher will be grateful to whoever can explain gravity through the laws of mechanism. So, I mean, the motto behind Lesage's attempt to explain gravitation as mechanical is because, okay, it is stated in the Leibniz-Clark correspondence, it is explicitly stated by Clark, and as we all know, well, the replies that Clark gave to Leibniz were almost dictated by Newton. So we have here also two kinds of matter. I already presented these famous corpuscles ultramondanes. And the ordinary matter is highly porous, and Lesage describes it like having geometrical forms, and it is more or less like empty cages in which the ordinary matter is only in the bars. So it is highly porous because it's like a cage, and we only have the matter in the bars. And the cause of gravity is because the ultramundane corpuscles are hitting the bodies, and when two bodies are hit, they create a screen effect, avoiding that one body is hit in all directions, but these corpuscles, and then they attract each other because they are pushed by the impact of these corpuscles. And he has also this demonstration of the inverse square law. The corpuscles follow the law of inertia. They move rectilinearly in a uniform motion and very fast. And the ordinary space is mostly empty. And if we have an isolated body on space, the body would stay still because it would be heated by corpuscles in all directions, and so it would not move. And he thinks that this is clearly in the line of Newton, because when we read the Principia, it is clear that gravity is a kind of a relational property, because if there is one body, there is no gravity. We need at least two bodies attracting each other. So this is an explanation of why a lone body, an isolated body, would stay still and not move. And the argument of the inverse square law is an algebraical argument, and it involves the density, the number of corpuscles. So the idea is more or less the following. Okay, we take into account the ultramundane corpuscles hitting on a body, and then Lesage uses this geometrical argument, which is based on Archimedes' the sphere and on Euclid's elements. So the point is that if we consider, like in this picture here, that the body, the ordinary body, is in the center, and it is surrounded like by spheres. Okay, this is just a geometry or geometrical imagination. And then the nearer and the ultramundane corpuscles will travel to hit the body, because they are traveling very fast in every direction in a straight line. And the nearer to the body, the more corpuscles would be in the sphere. And this is just normal, because the bodies, these corpuscles would have traversed the first sphere, and here are more separated, here are closer, and here the density, the number of corpuscles, is higher than in the outer sphere. So the nearer to the body, the more corpuscles would be, and since the corpuscles in the closest sphere have traversed the others, so the density of the corpuscles would be bigger in the inner sphere. And this density is more or less equivalent to what we call the gravitational force. And it is the density of the corpuscles in the vicinity of a particle of matter is bigger and decreases inversely proportional to the square radius of the sphere, of the distance. And this is inspired in an inverse analogy with the dispersion of light. The dispersion of light in a sphere was well known at the time, and we know that near the sphere there is more light, and it decreases inversely proportional to the distance. And also, if the body is very massive, Lesage says that its particles will be together, and it will receive the impact of many corpuscles, and the gravitational effect will be bigger. So it is proportional to the mass. And if it is not very massive, its particles would be far apart, and it would receive the impact of less corpuscles. Here is more or less the way he explains the proportionality of the mass, if I get this right. Okay, so from his Lucrèce Newtonian, he says, my aim is to show that if the earliest Epicureans had possessed as just ideas on cosmography as those of several of their contemporaries, which they neglected, and but a portion of the knowledge of geometry which had then been attained, they would in all probability have easily discovered the laws of universal gravitation and its mechanical cause. So here the knowledge of geometry is actually one of the keys. And we can extract a useful consequence for the advancement of physics in spite of the greater preference for a posteriori researchers. A priori ones are not to be wholly neglected, since they may greatly accelerate the success of the former. Let us clearly understand that such speculation is only permissible for the sake of occupation when the skill and patience with new observation and experiment required are lacking. So the search for a mechanical cause inspired in Epicureans is also another key, but also this plea for a priori research, but only when we cannot make observations and experiments. So the physical consequence is that he explains in some way the mass dependence of Newton's law, and he considers that the theory can be applied to cohesion, to elasticity, to optics, and of course to chemical affinity. It's what he did in one of the works. The reasons are, of course, the commitment to mechanics, and one of the keys is the improvement of Newton's method by using hypotheses. So as I said before, he and his disciples consider themselves as the true heirs of Newton because they made theirs the program of a search of a cause, of a mechanical cause of gravitation. He insists that Newton also uses hypotheses, although that Newton says that he didn't. And he insists on the idea that sometimes, and this is, I think, interesting from a methodological point of view, hypotheses remain mainly conjectural, that we not always prove all hypotheses. It's like, I try to think this in an analogy with the ideal gases, okay? We use the ideal gas, but it is just a conjecture that we use for other things. So maybe hypotheses can remain in a conjectural level, as if not everything in natural philosophy have to be just true or false. This preference of speculative physics over experimental physics is also kind of weird on a methodological way. He considers speculative physics as universal, whereas experimental physics is not universal. And of course, there are some problems because we can ask if these ultramundane corpuscles do affect each other gravitationally, because they might have a mass or so, okay, it is clear that they interact with ordinary matter, but do they interact among each other, and how can we calculate this? Also, that we have two kinds of matter, and here I would also say that at least we have two kinds of matter, because then he introduces an ether to explain magnetism, so maybe we have three or even more kinds of matter, who knows. And of course, it is a great problem that this is a highly speculative theory and there are no experimental results. And considering the methods, of course, again, he uses analogy, the idea that light passes through diamonds, and then the analogy with light to establish the inverse square law. His method is hypothetical deductive, and he is a critic of experiments. For example, he criticized Galileo's experiments because he considered that they were susceptible of many interpretations, and that might be a problem in natural philosophy. As I said before, he corresponded with much of the intellectual elite of the time, with D'Alembert, Lambert, Euler, Boscovich, and actually they all acknowledged that he had proved the possibility of a mechanical explanation of gravitation. So they recognized that it was the best mechanical theory, but they all rejected it because they considered that there was these ultramundane corpuscles were highly mysterious and actually highly speculative. Later on, the theory was criticized because of the use of hypotheses, but still, even at the beginning of 19th century, at the end of 18th century, beginning of the 19th, some of them, some famous physicists like Lichtenberg praised the theory and recommended it to his students. Okay, and now I come to the final remarks. I'm more or less on time. Okay. Newton's theory of gravitation was, as Van Lunteren says, was built on the foundations of mechanical philosophy, but it also seriously affected this foundation. And as I said, there are some problems in Newtonian concepts led to modifications in order to ground them ontologically and philosophically. Euler and Lesage's theories could be considered Newtonian or non-Newtonian. I decided to use non-Newtonian approaches, but as I said, this can be also Newtonian approaches. Why? First of all, because it depends on which parts of Newton's work we consider. No, he left the question open to the consideration of his readers. And also because Lesage declared himself as a Newtonian, although some of his contemporaries consider that he was not, and Euler used Newton's mathematics to develop also his theory. So depending on which part, this can be considered Newtonian or non-Newtonian. And by providing alternative approaches to natural philosophy, they all contributed to develop concepts in order to handle problems and to understand the way nature works. So the idea is not only to see them as forerunners and so on, but to be how different authors contributed to the development of important concepts that were used in science. And both Euler's and Lesage's theories promoted the use of analogies and hypotheses, which was actually well grounded. Some authors say that Newton's criticism of vortexes was not really devastating, although we have seen that these are not, nor Euler nor Lesage are vortex theories, they are different. But with these theories, I think that more or less we can say that there were good reasons to think about a mechanical cause of gravity, and thus this cause was provided. And there were also good reasons to use a hypothesis. And I think that one can say that there are still interesting controversies in the methodologies used by the scientists in 18th century. these methodological controversies can actually challenge some classical conceptions of science, because, as I said, hypotheses were not despised by all self-proclaimed Newtonians and neither by other authors. And the ether was meant to be a serious concept in classical mechanics, despite some current presentations that show that it is a metaphysical idea in which physics was embedded. When one looks some physics books, sometimes it is presented as a metaphysical residue coming from past centuries. Now we are rid of metaphysics, and okay, actually it was a serious concept. And here is for another time. This is actually, as I said I will present at the end my second reason to study these authors. And my second reason to focus precisely on Euler and Lesage is because versions of both theories were considered together or separately at the end of 19th century by all these authors. So some of these authors proposed corpuscular models of the ether to explain gravitational attraction that are variants of Lesage's theory. Others propose hydrodynamical models of gravitation, more inspired in Euler's idea. And these were actually more problematic because they require two mediums, an elastic solid for light and a fluid, and a subtle fluid for gravitation. William Thomson, Lord Kelvin, and also Tait supported Lesage's theory for some time and provided it with respectability at the point that it was highly discussed in the last third of the 19th century. And to Tolbert Preston, Lesage was the perfect theory, since he considered that there was an analogy to be done with a kinetic theory of gases. And kinetic theory of gases to Preston was the key to explain of all phenomena. And Hugo von Seeliger, who was the chief astronomer of the Munich Observatory, used the theory of Lesage to state that this theory can explain some gravitational absorption to avoid the famous gravitational collapse that Newton's theory could lead to. The theory was also criticized and studied by Maxwell and Poincaré. Poincaré also criticized Kelvin's use of the theory, and some people studying radioactivity use Lesage's theory also to make analogies. And that's all I had to say.